Right, in this video we're going to be talking about annihilation. I'm just going to go through a simple example. This is basically when matter meets antimatter and they both collide, and annihilation takes place. Two photons are emitted as a result. At this level, A level, you are meant to know about the different energies involved and how energy is converted from one form to another. So, to begin with, we're going to start off with a proton on this side and a neutron, and the antiproton on this side. So we're going to write the symbol. So proton, antiproton. Both of them have the same mass. The only thing that's different on these is the charges. So the proton we know has a positive charge. The antiproton will have a negative charge. We know the mass of this proton is 1.673 times by 10 to the minus 27 kilograms, and it will be the same for that. So we can calculate the energy or the rest energy of a proton using this equation. E is equal to mc squared for both of them. And as you might have seen already, both of them will be exactly the same, because the only variable that can change is the mass, and for annihilation both the masses are the same. So what we're going to have is, to work out the rest energy involved here, we're going to do 1.673 times by 10 to the minus 27 times by 3 times by 10 to the power of 8 squared. So that's the speed of light squared. That gives me a value. This is from a previous example or a previous video that I did. We find out that the rest energy in joules is 1.5057 times by 10 to the minus 10 joules, which gives us 941.0625 MeV. Most A-level questions you are expected to convert, even in the annihilation questions, from one form of energy to another. I'm just going to work with this today. 1.5057 times by 10 to the minus 10 joules. So that's what we've got. So we've got two lots of it. So we're going to do 1.5057 times by 10 to the minus 10 times by 2, because there's two lots of them. Both of these actually come together like this. So this will head that way. They both attract each other, and they basically annihilate in the middle, releasing two photons. Each photon has energy hf. That's the way we calculate the energy in terms of a wave, because these are photons, and photons are they're part of the electromagnetic spectrum. So that's what we've got at the moment. So if we do that times by 2, this is the first thing we're going to do. Right, currently there's two lots of them. We've worked out how much energy we have when we combine them together in the middle. So that's the energy of the system over here. That's that. So what we do now is, half of the energy gets taken away by this photon, half of it gets taken away by that photon. So what we're going to do is we're going to go back to square one. We're going to say 3.0114 times by 10 to the minus 10 divided by 2. We end up with that number, 1.5057 times by 10 to the minus 10 joules. If you look at a simple example, you don't have to do times by 2 and then divide by 2. You can just look at it and realise one will be responsible for one of them. So what we do now is we can work out the frequency of one of these photons using E equals hf. Rearrange it. E divided by h is f. So therefore we're going to have 1.5057 times by 10 to the minus 10 divided by 6.63 times by 10 to the minus 34. And we get an answer. We get 2.27 times by 10 to the 23 hertz. So there we have it. We can actually do this for any particle. We can do it for a neutron, anti-neutron coming together. We can do it for electron, anti-electron, or the positron coming together and creating an annihilation effect. It's actually very simple. The next example we're going to look at is actually a more complex example where we take into account kinetic energies as well as rest energies. Thank you.